Hello and welcome to Cambridge, Massachusetts. Tonight we have a very special guest, Alessandro Vespignani. He's a professor, the Steinberg Professor of Physics, Health Sciences and Computer Sciences at Northeastern University. And if you think about it, health sciences, physics, and computer science sounds like things that might maybe not relate in the beginning, but when you learn about the research that Professor Vespignani has been doing, it all gonna sound very natural. So I would like to start a conversation tonight talking a little bit about one of the things that you've done. You've done some work that has become, in the last 10 years, basically classic in what it is epidemiology. You were able to marry the field of epidemiology with the field of networks in a very impressive work. But before we go there, I would like to please hear from you. What were people thinking about before you combine networks and epidemiology? How were the way that people were approaching the epidemic spreading, and what were the implications of this approach?
Well, you think about epidemics, you think about individuals, and where individuals are in contact, they transmit the disease. So an infectious individual in contact with a susceptible individual, a healthy individual, can transmit the disease. This is a process in which, of course, there is a lot of biology. There is the property of the virus or bacteria, the pathogen that enters. But you can have a kind of coarse-grained description in which you have these individuals that are like atoms that wander around. From time to time they are in contact, and from time to time they can infect each other. So initially, when people started to work on epidemic modeling, on the way we can mathematically understand how an epidemic spread, they were considering all these individuals like a gas of particles somehow, that in which you have these random events of meeting, and the disease transmission was basically occurring during those random events. Of course, those models were opening the path to a lot of very, very interesting understanding for the dynamics of the disease. It's possible to basically write down the basic descriptive equations for the evolution of an epidemic in a population. And as time was passing by, people realized that, okay, the dynamics cannot be so simple. Individuals have recurring patterns. You are, of course, every evening you go back to your place, you have your family, so you have an household structure, and then you have your workplace. Some of us have a lot of contact, some of us have much less contact, but somehow it's very difficult to introduce all those elements in the description of a disease. And so most of the basic epidemiology was built on the fact that there were basically a few classes of individuals, more or less with similar properties. One of the main results in epidemiology is the concept of epidemic threshold. So if the pathogen is not fast enough in going from one host to the other, so it doesn't have a transmission rate that is large enough, the epidemic cannot take off. In order to characterize that mathematically, what epidemiologists use is what they call the reproductive number. So you imagine to have one infectious individual in a population, and then you say, well, during the infectious period of this single individual, how many other infectious individual it will generate? So somehow this is like a branching process. How many secondary case each infected case will generate? For the epidemic to spread, this number must be larger than 1. That means that you will have a kind of exponential progression of the epidemic. And this reproductive number must be larger than 1, and defines then the concept of epidemic threshold, because the property of the virus must be, or the bacteria, must be such as that this number is larger than 1. And so that defines what we call the epidemic threshold. This is a central concept in epidemiology, because this is also the way to attack viruses or diseases in general, because what you want to do is to reduce the spreading rate of the disease below that epidemic threshold in order that somehow you are able to eradicate the disease from the population. One way to do that classically is to vaccinate individuals, because since there is a certain fraction of vaccinated individuals in the population, the disease will have a reproductive rate that will go down. And of course, there was a lot of mathematical epidemiology based on that concept, and you can start introducing different class of individuals, the structure of the households, and see, you know, what is the effect of basically of the property of the system on the epidemic threshold, as well as many other dynamical properties of the system. One point that was crucial in the work I did initially was the fact that I was focusing mostly initially on the spreading of a special kind of pathogen that are computer viruses. And when you think about computer viruses, you don't think about the regular population. You think about computers. Computers are connected through cables, or you think about viruses that are spreading by emails. And so the first question that we start to ask ourselves was, well, you know, what are the properties of those systems? Are they like the one do they have the homogeneity that we think of those systems? So we can say that each user or each computer is more or less likely, is more or less like all the others one, or there is a large heterogeneity in the system. And this is where I approach networks, and this is where I did start to do some work on the analysis of networks, and we realized that in the internet, in the exchange by email, the things are completely inhomogeneous. So you have a wide variety of individuals. Some of us send a very few emails, some computers have a very few connections, and some of those computers instead have hundreds of connections, and some of us are, you know, have huge address book with hundreds of individuals that we use to correspond with. And even more interesting, and this is the results found in the area of complex network, is that actually there are not just classes of individuals, but there is a kind of continuum of individuals. So we are very far from what we call the normal distribution for the statistical properties of those systems, but we have all possible kind of skewed and scale-free properties and strangeness. And the idea was, well, if we want to model computer viruses, we have to take into account those strange features, so those kind of exotic features, if you want. And we made a very simple models in which we were measuring those the biological or mathematical biology model for the spreading of diseases with the complexity of networks that we were observing on the internet. And we were just working with my colleague Romualdo Pastor Satorras, that is now in Spain, and our expectation was to find some deviation from the usual results. So of course we introduced more details in the system, we introduced more heterogeneity. This probably will change the value of the epidemic threshold, or maybe perhaps the shape of the evolution of the epidemic in the system. And we did start struggling with the fact that we were not able to find an epidemic threshold. So we were creating a synthetic population in the computers, and we were doing numerical experiments to simulate the evolution of the epidemic on those systems. And we were observing that even for these diseases with very, very low transmissibility, the epidemic was always able to somehow pervade the system. And that was at odds with any somehow mathematical results. And that's because we were working with really extreme heterogeneous populations that were characterized by complex networks. Finally, after struggling with those somehow counterintuitive results, we found a way to mathematically describe those systems. And we observe basically the lack of epidemic threshold in very large systems with very heterogeneous properties. That's something that is change a lot your way to look at the epidemics in those systems. You don't have anymore this epidemic threshold. You don't know where to push the system. You don't know where and how to perform immunization policies, and somehow you have that those viruses are always somehow spreading, and they can be endemic or generate a large outbreak in a population. These results was somehow the starting point for a lot of work in that area, and for the that was studying the extreme consequences on dynamical processes in complex networks.
So that's a very deep result. If I can recap a little bit, you said that in the beginning people was looking at populations like very well mixed populations, like a box of atoms. You made that analogy, like a box of balls that is being jiggled, and the disease was being transmitted from one to another more or less randomly. So in a way, there were models in which people have assumed away the structure of society, they have assumed away the networks that we form, they have assumed away the way that we organize ourselves spatially and whatnot. And when they did that, they found this result that there was an epidemic threshold, meaning that if the disease was not spreading fast enough, basically it was not going to spread at all. Now, you guys find that when you relax only one of these assumptions, because there are many assumptions. There are assumptions about the space, there's assumptions about the strength of the ties, but you said even if you connect people simply in a network, but if that network has a particular structure in which a few individuals are highly connected, this epidemic threshold is going to vanish. It's not going to change by a little bit, but actually it's going to go to zero. It's going to disappear. So that's I think, a very powerful result. And then it shows you that as you go forward, maybe all of these other assumptions that we have, when we relax them, we can expect not only small deviations from what we know, but radical difference. So after that, I know that you have been looking at space, and you have been looking at different factors that affect epidemics. So can you tell us a little bit of what other assumptions you started to relax after that?
Well, you start to study all the possible difference that our daily patterns can introduce in a disease evolution, and so the fact that we might be more clustered with people at work, with people in the household, the fact that actually we have fluctuating connection, we have we don't always see the same people, and of course also we introduced and we did start studying the the complexity of the disease itself, and so we went to we did start to push on a realistic description of the disease. And one important point to say is that why initially the things were somehow confined to the realm of computer viruses, where we had data on networks and our interactions, because they were recorded on email logs or just computer connectivity maps. A lot of other studies have shown later on that even our social interaction, so our daily contact pattern with the rest of the world are very heterogeneously distributed. So there are some individuals which are hubs and some individuals which are more at the periphery of those networks. And so somehow the results that we had about the complexity of the network married with the epidemic spreading that were relevant in the computer world become more relevant also in the social world. And pushing on those analogies, we did start to say, well, we can go into a more and more accurate description of those diseases in what we call a data-driven approach. So the idea was, okay, let's introduce not just the contact pattern, but just introduce the timing of the contact pattern. Let's tag individuals so that we know that they have 2 kids, 1 wife, that they do a lot of work in that place, that there is the geography. At that point, you start to somehow recreate a synthetic world in the computer that is more and more realistic. And this is the way in which I think there is a lot of the way to look at the world of a physicist. As a physicist, we are used to take the law of physics, the law that governs atoms, and we put in a computer billions of those atoms according to the physics law, and we are able to predict the properties of materials. We can do marvelous things in the area of weather forecast by looking at huge integration of meteorological equations with real data. So somehow a physicist has in mind that through computation and statistical laws and natural laws, you can achieve predictive power. And that's something that is, at a certain point I did start thinking, is how we can achieve predictive power in those areas in which we have a mixture of natural systems, infrastructures, and a social component, so what we do. And, you know, today, you know, I knew we were going to meet and have this nice chat, but you know, I went on the web and I just noticed that it was going to snow, and so I prepared my day for that because I know that it was going to snow. And of course, it might be snowing a little less or a little more than expected, but somehow, you know, weather forecast works. Now, if you think about the complexity of the system and what is behind the scene of weather forecast, you start thinking, why? Well, we can do that also in different areas. Why was the opposition to the idea that we can achieve predictive power in techno-social or socio-technical systems? There is a debate of what the two words is the most appropriate. Were basically true. The first one is that, well, the social atom, each individual, is not like, you know, an atom in physics. So we have a very complex psychological and cognitive dimensions. We interact, we change our mind, we have the free will. Society is governed by leadership, by people that acquire leadership through discussion, through consensus, and so, you know, this is not something that you can put in a computer. And the other objections were, okay, it's almost impossible to get the data for billions of individuals on the scale that we would need to do.
So even if you can do the prediction, you're not going to know if it's right or not.
Yeah. And now, you know, in the last 20 years, probably everything has collapsed, and mainly for two reasons. The first one is complex system science taught us that, you know, you don't need to introduce all the complexity of a system to create emergent phenomena on the large scale. So if you take simple interaction among two individuals, but then those simple interactions will never generate something interesting. But if you put millions of individuals that interact according to those simple interactions, you can create emergent phenomena with enormous complexity. We see that every day, you know, fish schools, birds that flocks, you know, termite, ants. So this is what has been called that, you know, complex system science killed the myth of the ant queen. So the fact that, you know, to achieve certain organization, you need a leader, you need a hierarchy, you need specialization. You know, simple interaction can create phenomena. And so what we can say is that, well, if we grasp the essential element of the social atom, what is somehow measurable and what is somehow predictable in what we do, and we do plenty of things which are predictable, then possibly we can develop statistical laws for simple interaction, and then, you know, start having a construction, mathematical construction that allow us to understand the social aggregate state made by millions of individuals. This seems like a dream of a physicist. In some cases has been called social physics, now it's called social computational sciences. But if you go back, you know, a couple of centuries and you read the last two chapters of War and Peace by Tolstoy, he's explaining that, you know, that history is governed by collective phenomena. And, you know, the leadership is somehow the expression of those collective phenomena. It's not the leadership that generates those phenomena. And interestingly, in the last 20 years, we were also able to acquire the data that we need to establish the basic interaction rules among the social atoms, and also validate the models that we do. You know, nowadays we live with a mobile phone, and you know, we record traces of our mobility every day. Every record is digitalized and we can access those. We live in a world of pervasive technology, sensors. We live immense number of traces on the internet of our social interactions, our conversations, political attitudes. All those data creates layers that somehow define a kind of social tomography that allow us finally to construct those synthetic worlds, and we can think to achieve predictive powers, or at least anticipation on the state of the system in the techno-social arena. Now, what we decided to do is to start with infectious diseases and to create large-scale models for the forecast of infectious diseases, because somehow that part is the easiest, you know, because the social contagion might be a very complex phenomena. So I have an idea and you have to absorb that idea, there is your peer pressure, etc., etc. When we talk about biology, we talk about a virus or a bacteria, well, the transmission is a somehow simpler phenomena, and then a social contagion phenomenon. And so we went into the study of the spreading of emerging diseases. We did start to accumulate data on human mobility, human contact patterns, and we took the challenge to say, well, we want to achieve forecasting power. And we did a lot of work on previous epidemics, what we say, you know, the study of historical epidemics. So we recreated a synthetic world in which there are many of those layers describing the society. We have precise data on census and demography all around the world, mobility of people around the world, the local mobility. And then we can simulate the introduction of a disease in that synthetic computerized world and see how it spreads. And we were looking at past diseases like you know, the SARS 10 years ago and things like that, to understand the limit of reliability and predictability that the model was achieving. In 2009 we got the first pandemic of the new century, and we had even the possibility to test in real time those kind of approaches to the prediction at this point, the real prediction of the future unfolding of the pandemic, of the H1N1 pandemic in 2009, with those computational approaches. And actually what we got are very encouraging results. We were able to predict basically the epidemic peaks months in advance, just by looking at basically at the worldwide evolution of the epidemic in this synthetic world. Of course, you need to integrate large mass of data, you need to have supercomputing power, but it's something that is not out of reach. Of course, we face now a few really tough challenges. At the moment that you achieve somehow a level of prediction or predictive power in a social system, you become part of the system, because the information, the understanding that you generate, the prediction that you generate, get absorbed by people that start to react and adapt to that information. The classic example I can give is that if we have weather forecast about today's snowstorm, the snowstorm doesn't care about the fact that we predict in advance its occurrence. If I will predict in advance that there will be a devastating epidemic in the country, well, people will adapt to that information, and somehow your prediction becomes part of the system. And this is a feedback mechanism in which we have still to do a lot of work. We really need basically from the basic formal models to introduce those kind of feedbacks. We need to have data that allow us to parameterize those models. We need to have a real-time monitoring infrastructure that can gather data on the adaptation of people, and somehow close the loop that we need to have a full consistency in the predictive work.
So you see that the future goes there, that there's a fundamental difference between the prediction of a natural system and the prediction of a social system, because in the social system, actually, the agent who's part of the system reacts to the fact that a prediction has been announced. Yeah. And this could be the stock exchange, this could be traffic. You know, when you announce that there's going to be a traffic jam in some place, people is going to find another route, and they're going to create a traffic jam in the alternative route as well. Yeah. You know? So I know that, as you just mentioned, you know, you have been working in these predictions, and for example, in the last pandemic, you mentioned that you were able to predict the epidemic peak in advance. You know? Now, when you make that prediction, we live in a world in which nowadays we do not have this, you know, global broadcasting system of predictions, but I'm sure that there were some people that were more maybe politically connected that you know, probably saw this as something interesting and worth considering and came to you. Now that you have developed the techniques and the tools to make these predictions, how is that interaction going? How do people that is interested on using this on the world, thinking about it, on the possible uses that they can give? What is the application world?
I think, well, where the area where you can have the largest impact with those kind of systems is policy making, because of course you can provide information to the policymaker of what will happen to the system. Then the policymakers wants to, in many cases, change the evolution. You want to mitigate, you know, an epidemic, or you might want, for instance, enhance the spreading of some information or the adherence to certain public policies. Of course, what we do is to provide them information and a tool that gives quantitative insight on what could happen. But then the policymaker has a lot more to face. There are a lot of political issues. There are a lot of resource constraints that you have to consider. So I think it's a way to develop, it's very important to develop a dialogue between all the stakeholders in the problem. It has to be, well, we have to say something. It's you know, the idea, in many areas, the idea that you can have computational approaches that have predictive power is something that is really new. And so people are skeptical. I think the last pandemic, the H1N1 to 2009 pandemic, was a good example in the health and infectious disease arena, because policymakers, agency realized that, you know, it is possible to get really a lot of real-time information from modeling, computational modeling. There were many teams involved worldwide in that effort, and I think there is now more and more attention to what we can achieve with those kind of approaches. I think that in other area, probably we have still to break ground. We have to create success stories that allow people to trust more the simulations and the predictions.
And ultimately, do you see that that information has to be channeled to a policymaker, or would it be a possibility to give it directly to the people?
That's a hard choice, and this is a matter of how much you want the prediction to be, how to say, fed to the systems, and what could be the effect of that. You don't want to create panic. You don't want the people to start, you know, going and you don't want to introduce social disruption because of the information that you provide to the public. At the same time, you want to provide as much information is needed, and this is where, you know, really the policy making enters. And we as scientists that we do how to say, the technical part, have to be very respectful of the decision of the policymakers and all the implication, the political science that is behind that. It might be dangerous or not. There are also many critiques to those approaches immediately, because you can say, well, you need data and you provide predictions on individuals. You are somehow intruding the life of people. You are doing things which goes against you know, the privacy and the ethical guidelines. I would, you know, it's important to assure people that, you know, those kind of approaches do not focus on the single individual. none of us has in mind that we will have prediction on the individuals, as well as when you do weather forecast, you don't predict the pattern of a water molecule or of a snowflakes. You just, you create prediction for the system as a collective system, and this is what we do in socio-technical systems. So we don't enter we don't break those rules, and of course there are, however, somehow other dangers that as anything, you can use. Science for good things and evil things, and of course, if you start to understand how you can create collective phenomena, social ordering, or introduce you can start anticipating what could be the outcome of certain dynamics in a population. You can start to manipulate. You can start thinking about manipulating those processes, and of course that might not be benign in the end. And so these are, of course, there are still issues, and we have to be very careful as soon as we achieve predictive power on a systems. That's power indeed, and if we achieve power on a social system, that of course is something that has to be handled very carefully.
That's extremely interesting. So then I do think that we all look forward to a future in which there are going to be predictions, but I think we even look forward more not to the predictions of the future, but actually how society is going to deal with the fact that there's going to be a world in which there are going to be predictions in the future. Now I wanted to turn the conversation in a different direction. And you, as we started, you are a professor of physics, computer science, and health. And now probably for everyone is clear the combination between these three, because you have a deep theoretical understanding of networks and of dynamical systems, but you have been applying that using computational methods to the spread of infectious diseases. And that's not a very curious combination. You don't go anywhere and get a PhD or a master's on that. It's a very strange combination, and probably behind that there's a very peculiar life history that got you there. So I would like to know how that life history got started. Like where did you grow up, and in your childhood, how did you started to get interested in the things that eventually became your life passion?
Well, actually, initially, I did start to think about physics, and initially it was biology, and then I became fascinated by physics. I think I was 12 or 14, something like that. And what was irritating me is that when you are a kid and you are reading about science books, they tell you about the atom and physics, but in a way that is so simplified that you say, well, this cannot be like that, you don't believe. And that was really like, it was really bothering me. I said, I want to be a physicist because I want to understand those things. Somebody will, quantum mechanics it seems something very strange. Then I realized by studying physics that even now quantum mechanics is an act of faith. But in a way that was that led me into into studying physics.
And that was in Rome?
And that was in Rome because I'm originally Italian. And after that, however, in physics, instead of going into quantum physics or high energy physics and particles, that is, of course, always when we are kids, we think about that. I got fascinated by collective phenomena. So how from two atoms we can understand, what we see around us. If you take two molecules of water, you will never understand that there is water, ice, or vapor. And I did start to say, well, I want to understand how that happens, how those billions of molecules together can create those wonderful things. And then I entered into statistical physics, and I also in that area at that time there were a lot of interest for materials that have fractal properties and very complex shapes and nonlinear systems. And after my PhD, I went to the United States, to Yale, to work with Mandelbrot, that was working on fractals. He's the father of fractals, fractal geometry. And I did start to somehow to get more and more interested in complex systems and in a way into interdisciplinary applications. So although I went back to the Netherlands, and then I've been working at the International Center for Theoretical Physics, that is a UNESCO agency, for some time, doing research on physics, on materials. I was always somehow interested in things that were at the, somehow what we call interdisciplinary physics. And I was studying diffusion processes and things that are closely related to epidemic spreading. And then, we go back to the start of our conversation. I did start wondering what was the effect of complex network in it, and I got more and more into the study of computer viruses and computers and the internet. What is the shape of the internet? What is how we can characterize a huge network like the internet? And somehow naturally I drifted into computer sciences, and I remember I went to work at the CNRS in France, in Paris, and I was in a laboratory for theoretical physics, but I was studying the internet, and that was peculiar. So at a certain point I got an offer in the United States from a School of Informatics and Computer Science at Indiana University, and naturally I moved my activities into a computer science somehow how to say, environment. I never realized, I never planned for those kind of moves. They were natural. And then I did start in a school of informatics. I did start to apply computational tool to epidemiology. I did more and more data-driven things. I get more and more interested in how we can interface computational tools with policy making, and that has led me naturally to a department of health sciences, and now what is special, I think, in the Boston area is indeed the fact that if you do interdisciplinary research, you can be in a place where you can be connected with very, very different worlds, and in a way this is not, it's not odd. For me, it's great to be a Northeastern in a way in which I can still be part of three different worlds that combine together, however makes sense. And it's strange. If I have to when I'm thinking about the path, I have to say that for sure it's something that was so natural. It was like, there is a history in the research that you do that drives through these different areas. Of course, there is a kind of obsession for getting something new. So you are in physics after many years, and approaching the internet is something that is refreshing, is a new problem, is something completely different. Then you go into epidemiology, is another different problem. So, and I think is how to say, keep you young. Every time you go back to, you get established in one area, and then you have to start all over again. You're like you're going back to be a kind of student. And you have to go through the textbook, and then you have to learn how to write papers or to do what is the language of that specific area. And this is very challenging, at the same time refreshing. It's like you start your careers many times, and at the end, however, you always bring in your backpack, in your imaginary backpack, all those pieces of interesting things that you have learned, and you can try to combine those pieces to solve puzzles, and I think it's a kind of natural things. You cannot force those evolutions. So.
And is there like a path that you're starting to explore now? That is, you've been now working in epidemic spreading for a long period of time. You've done, you've gone from the basic theory to develop basically like a SimCity version of the world in which you can simulate epidemics and predict them. And now I'm wondering if you're curious about other areas that you're looking to explore.
Well, you know, we get more and more interested in social networks that are more social. It's not just the epidemiology, but so, for instance, how can we describe social contagion, for instance, for knowledge, for ideas, for the emergence of consensus or political consensus. That is the step, the next step that bringing me closer to the social sciences, to political sciences, and you know, now you know, basically we created a lab with David Laser that is a political scientist, and so you have physicists, political scientists, epidemiologists all together, and I think that's probably the evolution, but you know, it's difficult to say where we will go from there.
So I think one question that I have to ask you, you know, given the colorful background, the place where you're not, everything, what do you think is going to happen with, you know, disciplinary boundaries in the future? Are they going to blur? Are they going to exist there? Are there going to be always boundaries, and there's going to be people that is mobile, but other ones that are going to be, you know, more established in each one of these different
I think that,
sciences?
yeah, this is a very good question. I don't know. I think that science will be more interdisciplinary in the future. So the big question that we have in our society nowadays requires multiple expertise, and not just cross-disciplinarity in the sense that you can apply different expertise to solve a problem. It's not just a matter of hiring some computer scientist as you know, guns for hire to solve a specific problem. It's really, you need to create different way of thinking that emerge by merging different areas, and to blur these disciplines, it's not easy. Although many people and all universities they tell you that they are, you know, they want to go for interdisciplinary to destroy the disciplinary boundaries and silos. This is not the case. It's a tough job. There is language barriers, you know, academic barriers. There is all the possible hurdles.
Yeah, and that's what I want to touch a little bit. What do you see the limitations that are going to make it hard to get there, to get to this like new renaissance, or to get to a place where
social structure. And academics is created, how to say, you know, well, many colleagues.
In your experience, for instance, like when you move from one area to another, is people from the area that you're moving into tend to be receptive, or is it?
Always skeptical. We are all territorial at the beginning, and we want to defend our boundaries and say, you know, why a physicist has to do, you know, computer science, why a computer scientist has to do epidemiology. Is that initially everybody doesn't want that. The reaction is always defensive. Then you start, I think, again, you have to be very humble. You have to start saying, okay, I want to learn things, but I can probably, the way I think is maybe a little bit different from yours because of my background, and this could create, you know, something different, you know. In many cases, you know, as in complex system, you know, more is different, and this is, I think, you need time to penetrate an area and to create a real interdisciplinary effort. In many cases, this interdisciplinary effort leads to the creation of new disciplinary areas, but I don't think that this is the future. We are really going to face problems in the near future that requires a systemic approach that is fundamentally different, and this is what we wanna go, and I believe we will go there.
Well, that's great. It was great for me to get those thoughts here at the end. I think it's very interesting also from the point of view of the community that we all form as academics, not only here in Boston, but across the world. You know, I think a lot of people probably has faced very similar type of challenges and issues. So it was a pleasure having you here, Alessandro. It was a great pleasure to learn about your research and to learn about your story. So thank you very much for coming.
Thank you very much, Cesar, for hosting me, and thank you very much for the very nice conversation.
Thanks.